We've now gone through the formulation and derivation of how gas properties change across oblique shock waves. In this video, we're going to look at some important results about oblique shocks that come out of this analysis. We'll concentrate here on the relationship between flow deflection angle, shock wave angle, and the oncoming flow Mach number. This is the expression that we developed. And let's just look at that expression again. So we have theta, our flow deflection angle. We've got beta, our shock wave angle, coming in several times. And we have m1, the Mach number upstream of the shock wave, coming in. We also have our ratio of specific heats gamma. We can look at this expression as allowing us to prescribe a flow deflection angle, and for any given value of upstream Mach number m1, we can determine what would be the shock wave angle beta. And here's a plot of that relationship. So here on the horizontal axis we have the deflection angle theta plotted from 0 to 50 degrees. On the vertical axis we've got the shock wave angle beta going from 0 to 90 degrees. And we have a series of curves here for different Mach numbers showing how that relationship varies. The Mach numbers plotted here, get rid of that, are Mach number of 2, 3, 5 and infinite. Let's pick a flow deflection angle, say around about 15 degrees. What we see is that there are two possible shock wave angles for any given Mach number. So say for Mach 3, there's a possible shock wave angle there, and there's a possible shock wave angle much higher up there. And if we go to higher flow deflection angles, say up just below 50 degrees, we see that there's actually no solution at any Mach number. So let's make a note. First important note is that for any Mach number m1 and flow deflection angle theta, either we can have two solutions, and we call those solutions the weak shock solution. And this is actually the usual situation. We usually will get the weak shock solution, and it occurs for low values of shock angle beta. The other is termed the strong shock solution. And this one is less usual, and it is for the high beta. So on our plot here, the low value that we had for the 15 degree deflection at Mach 3 would be the weak shock solution, and the high value would be the strong shock solution. And our other possibility, if theta is very high, is that we can get no solution at all. And we'll state that this way, that for a given m1, there's a maximum flow deflection angle theta max for which an attached shock is possible. So if we look at our plot over here on the right, we can pick for any given Mach number where that maximum angle of flow is possible for us to have an attached shock. And if we join those curves, those points on the curve, we'll end up with something like this. A curve that comes up like this. And below that curve we have our weak shock solution, and above that curve we have the strong shock solution. Let me just slide the screen down and make one more point about the shock detachment. Our plot shows us that theta max is smaller when we have a lower value of m1. So what this means is that for high Mach numbers we can get an attached shock for much higher values of flow deflection angle. So I can write that as we can get to higher theta with an attached shock for high Mach numbers M1. I'll slide the screen back up because there's another small curve that I want to put on the theta beta Mach number curve, and that's this dashed curve here. Everything above that curve has the Mach number downstream of the oblique shock being less than 1, and everything below that curve has the Mach number downstream of the shock being greater than 1. Now this curve is very close to our shock detachment curve, but it does show that there's a small region for attached shock waves where the Mach number downstream of the shock wave may be less than 1. But usually the Mach number downstream of a shock wave for a weak shock is greater than 1, and always for a strong shock the Mach number downstream of the shock wave is less than 1. So we'll move that screen down again and make a couple more points. So the first point is that usually the Mach number is greater than 1 downstream of a weak shock. And since the weak shock is usually the solution that we have, then usually the flow remains supersonic downstream of an oblique shock wave. But we'll also note that there is that small range of theta for any given Mach number where the Mach number downstream of the shock wave, a weak shock wave, can be subsonic. So it can occur, but it's unusual. And the final point I want to make here is that the Mach number downstream of a strong shock wave will always be subsonic. In the next video, we'll have a look at some experimental results from the Drummond shock tunnel at UQ, demonstrating how the flow deflection angle, if we vary the flow deflection angle, how the shock wave angle varies for a given Mach number.